here as a Kinetic Energy Recovery System. I'm a project manager, Nigon, and my partner is Patrick James, and faculty supervisor is Dr. Kamal. So the problem definition to our project is we wanted to build a scooter that operate efficiently in congested areas such as campus or metropolitan, because where you can frequently stop. And also we wanted to design a user-friendly kinetic energy recovery system for the user who doesn't have to have a lot of knowledge or easy to operate, and also that increase the mileage and travel distance. And we use the dual power supply, the primary and the secondary sources when implementing this kinetic energy recovery system. We're in industry that use this technology or introduce this technology was introduced in motorsports Formula 1, and this technology also introduced in the vehicle industry and transportation industry, such as train in a foreign country. The approach to our project is we were trying to implement a circuit that has multiple H-bridge, one for the primary and one for the secondary and one for the charging. And during the operation, we only charge the secondary sources, and also during operation, it alternates between the two sources when the secondary source is available. Design goal is we are trying to combine two sources of power to increase the range and during the frequent acceleration and brake cycles, and also we use more of the secondary source when it is available, because we thought that we thought that every time we do the operation, primary is primarily supplied to the motor, but the secondary is going to be charged in frequent stop. So the secondary is going to be charged, and also the smooth transition when switching between a primary and secondary batteries. This is our top-level design. As you can see in the diagram, the red line represent a single source mode. What it does is that basically single source mode primary battery will be used to power the motor. And the second picture is, as you can see, this is the dual source mode. The red line represents the primary source, and green line represents the secondary sources. When you actually look at this design, only one source is used at a time. This is the last one, the charging. The blue line represents the charging circuit. Anytime during the operation, anytime it stops it, only the secondary battery will be charged. Our project to the hardware design requirement, H-bridge must be able to handle the 20 amps, because failing to meet this requirement, actually not working the motor properly and damage the H-bridge. And also the voltage to input to the microcontroller must not exceed 3 volts, because the voltage cannot read the voltage above 3 volts. That there is some kind of mechanism that we have to create a circuit to readable range to the microcontroller. And the secondary source must have an advantage. For our advantage, secondary source has low threshold, and also it has wide range of operation. And also the main concern was the safety issue. We thought that we're using the nickel metal hydride battery. When we do the research, we thought that that was the safer than any other battery that's on the market. And we think that this was quite important, because since we're designing the moving device, there's in case there might be some kind of collision problem, and certainly we didn't want our scooter to explode because of the battery. This is the simple logic of how H-bridge works. Basically, as you can see, this green color just represents the one directional use, and H-bridge basically use the transistor technology to control the current from the power source, in our case, the two power sources, the primary and the secondary sources, and also the motor can move the current through the H bridge back to the battery charges. In our project, only the secondary charge. This is the sensor circuit that I talked about earlier. As you can see, the horizontal line, horizontal axis explain the input voltage, and vertical axis represent the output voltage. When you, during the simulation, when we create the sensor circuit, we thought that even though our primary and secondary battery is rated at 24 volt, we thought that it is important to go beyond the 24 volt in case if there is any issue. And as you can see, as the battery increases, it will not go above the 3 volts. This is the overall diagram of our design project. As you can see, there is a microcontroller, throttle, and LCD, and you can see 2 sensor circuits and then the H bridge. H bridge will work primary and then secondary and charging. And the throttle position is basically correspond to the scooter's speed, and the microcontroller monitors the throttle position and also display the all the information in LCD, such as scooter speeds and what kind of modes are in operation, and also the voltage reading.
All right, it's basically operated with pulse width modulation to control the average voltage going to the motor. So if we're at 50% throttle, there's only going to be 12 volts going to the motor, and it's going to run at about half the speed, half its maximum speed. During single source mode, where it's only using the primary, it'll show, you can see that on the oscilloscope, it shows that there's a primary source being used, and then across the bottom is just the secondary source being stuck at 0. Importantly, during dual source, when it's actually using being supplemented with the secondary battery, it shows that during the first part, we're going to have a lot of volts left in the secondary battery, so we're going to use a wider pulse of that and shrink the primary pulse. And over time, we're going to shrink the secondary source because there's less left in it, and we're going to have to extend the primary battery to still get the same amount of output. Our software is such that if you lift off the throttle, we're going to try and charge the secondary battery. But then once you get back on the throttle, it's either going to go into a dual power mode if there is enough power left in the secondary battery. Otherwise, it'll just switch and just use the primary battery until that runs out. This is our LCD display. It's not very this big, but this is showing the volts left in the primary battery. It's showing 10.5 volts, while we're in mode 2, which has, this is dual power source, and then we're at 22% throttle. And here's a demonstration of the scooter. Here we're going to go to the third marker in the view, and that's where we're going to start braking and then come back in that, and start braking at that marker, come back, and then just continue back out and do that. This represents a lot of times when you're in the city, you're going to have to be braking a lot more frequently, and then get back on the full throttle to the side. What we did is, to test it, we did 4 of these back and forth, and then went all the way down the street for a longer view, because assuming you get through the traffic, then you'll be able to go, and that would create 1 lap, I guess, of the. This shows the results of the course we did with the single source. We were able to accomplish 10 laps, almost 2.5 miles. And then the dual mode, we're actually able to go another lap further, or 6% more. On the final lap of with the dual source, we were only able to go through the short course enough, and then once we made that long stretch again, then it actually ran out of battery. This is our cost. We spent $450 and 160 man hours, contributions, and lessons learned. It's really helpful to find somebody in your field that can actually help you a lot. Teamwork, getting along with your teammate is really important, You're not going to get anything done by yourself because you have to integrate everything in the end. Get to assembling hardware as soon as you can, because then you're going to find problems. Communicate with your faculty supervisor regularly. It's important, he's there to help you. And then choose the components carefully. Make sure you're selecting stuff that's going to actually work. And if you don't, you're going to end up wasting money